right, as we get started today, classwork's on the board. Take just a few moments to work on these classwork problems. Pause the video while you work, and then resume once you are finished. All right, students in here are lightning fast. They're already done. So let's go ahead and take a look at these together. What did you get for g of 7, Quentin?
28.
28. We're going to square the 7 right here to get 49. We're also going to multiply the 7 by the -3 to get the -21, end up getting 28. Then for g of a -4, we had to do the same thing, plug it in twice. Here when we plug it in, Jamie, we have to get initially
a square minus 8a plus 16.
And then here we also have to plug it in, multiplying it by the -3 to get
-3a plus 12.
And then we combine like terms together to get
a squared -11a plus 20.
There we go. Questions on these? All right, looking at the next one, here we have the limit as x approaches 5 for the same function we had a moment ago, x squared -3x. One way, of course, we said we could work this is to try plugging in a 4 and then maybe a 4.5, maybe a 4.9, keep getting closer and closer to 5, but it's easy to just plug in the 5, right? Unless there's a reason you can't, but we can, so let's just plug it in. What do we get, Quentin, for the limit as x approaches 5 for the function x squared -3x? 10. No problem plugging it in. On the next one, however, you can't just plug in the 5, Jamie. Why not?
Because it's too complicated. Oh, it'll make a 0 in the denominator.
Yeah, they give you a 0 denominator. Also, by the way, give you a 0 numerator. Give you a 0 over 0. So in order to calculate the value, we said here again, go to that limit idea. Plug in the 4, plug in the 4.5, plug in the 4. Or the shortcut.
Or we could backwards forward.
Now we could factor the numerator.
X and x -5, 3.
And that does check out. And then once it's factored, cancel away. Now I can plug in the 5 if I want, and I get 2. What if you couldn't factor and cancel? What was the other option we had discussed? What?
To plug in a 4.9.
Well, right, okay, that was one method, okay, and it works. You would have figured out the 2 that way. Method number 2, the easy way, is factor and cancel. There was a third way, though, to get rid of the x minus 5. Do you know what it's called, either of you? Synthetic division, right? We could have put the inverse of the -5 in the half box, written down the coefficients of the numerator, and then, bring down, multiply, add, and that would give us the x -3 that way, and then we plug in the 5. So a couple of options that we had there. Certainly factoring, to me, the easier method. Questions on the classwork? Let's take at the homework then. Page 310, you did 4 through 6. You did 8, 10, and 12. 4 through 6, 8, 10, and 12. And let's take a look at these together. Number 4, you were determining h of 2, h of 0, and h of -2 if h of x is a x -2 squared plus 1. And this one looks a little more complicated, where it'd be harder to do in my head, so I'm going to take a moment to write that out. But h of 2, what do we end up getting for h of 2, Jamie?
1.
Just 1. Because the 2 minus 2 gives you 0, which when you square it is still 0. You put a negative, it's still just 0, so you just get 1. For h of 0, though, Quentin, what did you end up getting here? Number 4? I'm not sure what you... Oh, I see what you did. Okay. It's not entirely wrong what he did. Okay, so rather than plugging in the 2 here, subtracting a 0 and all that, he went ahead and expanded it out to get the x squared -4x plus 4 plus 1. Changed all the signs to get -x squared +4x, -4 +1, though I would have combined the -4 +1 to get -3. And so then you could plug in the 2. You'd still get a 1, though, here, because 2 squared, but you have to make it a negative. Again, it's not negative x that's being squared. It's just x being squared to get the 4. Then you make it negative. Then the 2 times 4 gives you the 8, and then the -3. So we should have gotten 1, but that explains why about 9 for your answer. So yeah, let's do it the easier way, I think, which is to plug in the 0 here.
0. Well, square. So 4.
4, but then we make it negative, and then we add the 1,
Negative 3.
-3. For h of -2, Jamie?
I got 5.
Well, -2, -2?
0.
Ooh. -2, -2?
Negative 4.
-4, square it.
Positive. Wait. 4. -4, so 16.
Positive 16, but make it a
Negative.
-16, then add 1.
-15.
-15 should have been our answer. And then finally, oh, that was it, just those 3. And then they said find the limit as x approaches 2. Well, the limit as x approaches 2 is h of 2. So again, it's just 1. Questions on 4AB. 4 part A and B. Does it make sense now? A little bit of trouble with that one. That's a much more complicated function. Number 5 is a very simplistic constant function. F of x is 5. So for f of 0, that means we plug in a 0 everywhere we see x. And what do we get for f of 0, class? 5. What about f of 2?
5.
What about f of -1?
5.
What about the limit as x approaches 0? There's nowhere to plug in the x. It's just 5 all the time, right? So 5 is the answer to everything. At least for number 5, that was the case. Number 6, also a very simplistic function. F of x is just x. So f of 7, class? 7. F of -1? -1. F of 0? 0. The limit as x approaches 14. 14. It's just whatever the x is. All right, so 4 was a challenge. 5 and 6 were insultingly easy. Questions? Let's take a look at number 8. Then we have the limit as x approaches -1 for 2x squared -2 all over x plus 1. And again, I can't just plug in the -1 because it gives me a 0 over 0, and that's no good. So, the numerator, what ought I to do? Factor out of 2 to initially get,
A squared minus 1.
but then,
Make that A squared minus 1. 2. Binomial. Or,
So BX.
yeah, difference of squares, I think is what you were trying to think of, turns into the sum and difference. So turn the difference of squares into the sum and difference. That allows me to cancel away the x plus 1. So I'm left with 2 times x -1. Now I can plug in my -1 and end up with an answer of -4. Our answer, because -1 is -2 times the 2 gives -4. Did we get that? For number 8.
I was close. I did everything else, but somehow I got a 0.
Okay. Questions? All right, let's take a look at number 10, where we have the limit as x approaches -2 for a 2x squared -3x -14 all over x positive 2. And what do we do here, Jamie?
We're going to factor spoil to get x and 2x positive -2, 7.
All right, and then we check the outer inner. Yes, it checks out. By the way, I already knew one of the two factors ought to be an x plus 2. I mean, surely, right? So you kind of cheat the system. I know it's x and 2x, so, and then I know it's plus and minus, so I'm going to put the plus with the x. I know it's probably 2 and 7, I'm going to put the 2 with the plus and the x, right, to allow me to cancel here. So it's really just 2x -7, plug in the -2, and what do we get as we evaluate?
-3.
-2 times 2?
-4.
-4, -7.
-11.
-11 should have been our answer there on number 10. Did you get that? Did the same thing as Jamie. You copying off her work? Number 12, we have the limit as x approaches -3, then x cubed plus 6x squared plus 11x plus 6 all over x plus 3. Quentin, thoughts? Yeah, this factoring is going to be not so nice. So here I'm thinking the synthetic division also. What goes in the half box? -3. The value the x is approaching, or you could say the inverse of the denominator. Either way, that would work. And then next to the half box,
1, 6, 7, 6.
there we go. It doesn't hurt to put the pluses in there. We'll bring down the 1. We multiply, class. Then add, multiply, add, multiply, add, and we end up plugging in x squared, x to the first, x gone, and now I can evaluate -3 in here, and I end up getting,
I had 0.
ooh,
I also had 0 because it got to be 0 in the denominator.
well, there isn't a denominator anymore. We took it out. Remember, when you divide away, this is all that's left. This becomes, if you will, the limit as x approaches -3 of x squared plus 3x plus 2. Make sure that's all showing up on the screen. Do we see that by dividing, that's what we turned it into, right? Like if I said, what's 48 divided by 6? You would say 8. Don't I need to divide it by 6 though? No, I already divided by 6. I already did what it said. I already divided by x plus 3. Don't put that denominator back on. Does that make sense?
Would it be 2?
It should be 2 for our answer. There we go. So 2 should have been our final answer. Questions on that? Questions on the homework with limits and function notation. All right, now all of that is leading toward actually starting calculus today. So there's a couple of big ideas in calculus, and one of them is this idea of slope. We know what slope is, 2 words, well, 3 words, I guess.
Rise over run.
Rise over run, that's what slope is, right? Rise over run. So for a linear function, right? Linear meaning straight line, it's very straightforward. I pick any point on the line, pick any other point on the line. If I want to know the slope, I calculate how much did it go up, how much did it go over, and I make a fraction out of it, right? I would take the change in y over the change in x, and that's all there is to it. But for a curve, now this isn't a functional curve, but for a curve, you understand there isn't a set slope, right? The slope would always be changing. For instance, if you were, picture you being a little bug walking around. Well, if you're a little bug and you're right here, you're looking that way, right? A little bug comes right now, you're looking that way. Keep walking now, you're looking that way. Keep walking over here, now you're looking that way. Do you see how the slope could be defined? By the slope of the line that is tangent at that point. So in your notes, if you write that down, the slope of a curve is defined as the slope of the tangent line at a given point. The slope of a curve is defined as the slope of the tangent line at a given point. Now what this means is that the slope is always changing. There's not a single slope for the function, but at any given point, there is a specific slope for that point. Does that make sense? Every individual point on a curve has its own predefined slope. So how would we figure out what the slope is? So step number 1, and I'm going to go and draw an actual function curve now. Obviously, we wouldn't be finding slope at any point on a circle. It's not a function. But for instance, maybe take the sine curve, right? Something like this. I mean, there you've got that curvature to it, okay? So if I wanted to find the slope, for instance, at this point, well, there would be, again, the slope of the tangent line. What is the slope, represented, remember, by the little m, of the tangent line? Whatever the slope of the tangent line is the slope of the curve at that specific point. Make sense? And again, that'll be constantly changing. Right here, it's pretty much like, that's almost a straight line, almost. And then here, of course, we see the slope like this, and then the slope like that. So we see the slope changing, right, along the curve here. Well, step number 1 is to pick a point, okay, that we're going to find the slope at. So we'll call this point P. Your second step would be to pick another point, maybe this point here that's pretty close by, call it P prime. Now I'm going to zoom in just a little bit here. We're going to pretend to zoom in, all right? Let's take this. Okay, here's my point P. Here's my point P prime, okay? Now you understand that the tangent is probably something like, maybe closer to this. Let's go with that line as being approximately the tangent. You realize that a line between P and P prime isn't too different, but it's different, right? Well, if the P prime were closer, do you see that this line now is closer in slope to that one? If the P prime gets even closer, this line's slope is even closer. Pick this point, now that slope is getting even closer to the true slope of the tangent line. The idea would have to be, you'd have to get P prime really almost infinitely close. Does that make sense? So that the slope of the tangent line, write this down, would have to equal the limit as both change in x and change in y approach 0 for the change in y over change in x. That's what slope is. It's change in y over change in x. But for the tangent line, given any 2 points, p, the main point that we're finding the tangent, the slope at, and p prime, we'd have to use the limit then as delta x and delta y both approach 0. Well, the problem is you can't use two variables, because we're tied to a singular variable in calculus because it's tied to functions. So instead of change in y, we don't do that anymore. We do change in f of x. Does that make sense? So we're going to just change that to f of x, but here's the thought. As the change in x approaches 0, that's going to affect a change in f of x as well, right? So I don't really need to worry so much about how f of x approaches 0 as much as the delta x, the change in the x approaches 0. So we can further simplify and say it's the limit as just the delta x approaches 0, because the other's going to have to approach 0 along with it, right? For the change in f of x over delta x. So far, so good? But let's think about what this change in f of x would be. Change implies there's a first and a second, correct? So change in f of x could be changed to f of x2 minus f of x1. Agreed? Whatever the function of x2 is, minus the function, so x1 being the x value for p, and then p prime has the has this other x value. Well, as x2 comes here, and then here, and then here, and then here, we see that this x2 value is getting closer, and as that change in x changes smaller, that change in f of x is also going to change likewise with it, right? Which is why we said we really just need to focus on the other. But we still have, that still hinges upon knowing a defined x2, correct? That's kind of annoying, because I don't really want to have to define where point p prime is. It'd be really nice if p prime could be, again, that infinitely close point to get an exact tangent as that limit works. So since we know that change in x is x2 minus x1, then we know that x2 would be equal to change in x plus x1. You follow the algebra? And in that case, we could plug that in there. And this gets us the equation in the form I want you to memorize it. This is called our first derivative equation. Let me write that term for you. First derivative equation. And it's that the slope of the tangent line at any point on a curve equals the limit as delta x approaches 0 for f of, and instead of x2, I'm going to replace it with delta x plus x1 minus f of x1 all over delta x. That's our first derivative equation. The limit as delta x approaches 0 for f of delta x plus x1 minus f of x1 all over delta x. Let's see how this equation works. Let's actually work a problem or two through together. Let's suppose we have a base parabola. Okay, so your most basic parabola is the one that has its vertex here at the origin and flashing all the way back to your algebra days, over 1 up, 1 over 1 up, 3 over 1 up, 5, and so forth. Remember that? All right. Now, we know the slope of the tangent when x is 0. It's this line. It's tangent, right? So slope is 0. But if we came right here when x is 1, well, this tangent line looks like it might be something like that, or maybe something like this. There's a certain slope to that line. The question is, what is the slope? So if I want to know the slope at that exact point, I need to know the slope of the tangent line when x is 1. Or in this case, x1 is 1, right? The that x2 is that infinite point we've got rid of, okay? So the function here, right, we would have said in algebra class, we have y equals x squared, or perhaps f of x equals x squared, and certainly we want the functional form here. Well, to find the slope of the tangent at the x1 equals 1, we would say we have the limit as delta x approaches 0 for f of delta x plus x1, but that's a 1, minus f of x1, which is 1, all over delta x. Make sense? The x1 becomes the specific x value you're looking for. Easy enough? All right, and then from there, we solve. Since the actual function, f of x equals x squared, well, f of delta x plus 1 means we have to plug that in for x. So we're going to have the limit as delta x approaches 0, and then here we're going to take delta x plus 1 and plug it into the function, because that's what it is. It's f of x is x squared, f of delta x plus 1 is going to be delta x plus 1 squared. Minus f of 1. Well, again, that means the 1 goes in there, so that's minus 1 squared, which of course we know is just 1. All over delta x. Now again, the reason we're using the limit is because you can't just plug in a 0, right? Well, let's follow this through a little bit. Let's go ahead and square the binomial. And Quentin, what would you get if you squared a delta x plus 1?
Delta x squared plus 2 delta x plus 1.
Good, and then we've got minus 1 at the tail end, all over delta x. Thoughts on the plus 1 and the minus 1?
0.
They're going to cancel each other away, aren't they? So all I'm left with is a delta x squared plus 2 delta x over delta x, but I'm not allowed to plug the 0 because you can't have a 0 denominator. What was the key to simplifying fraction in a limit situation? Factor. Since all that's left is this little piece here, how would I factor that?
Delta x and delta x plus 2.
There we go, factor out a delta x times the quantity delta x plus 2 all over delta x. And what happens? Delta x cancels. Now we're allowed to plug the 0 in, and we just get 2. So at 1, the slope of the line has exactly a slope of 2. Well, what if we came a little further and we came way out here somewhere? And we said, okay, well, what's the slope right here when x is 3? Well, we do the same thing, but now we would put in a 3 for the x sub 1. Make sense? And so we plug in delta x plus 3 gets squared, because that's the name of the game, minus f of 3, or 3 squared. And so that's going to change things just a little bit here. When I square the binomial now, I get delta x squared plus 6 delta x plus 9 minus 9. Notice the plus 9 minus 9 again cancel away. And again, I can factor out a delta x. But this time I'm left with delta x plus 6, which means, plug in the 0 for delta x, the slope here is 6. Rise 6, run 1. That's the slope of the tangent line. If I wanted to come back here at, say, negative 2, what's the slope of that? Well, in that case, my x1 becomes negative 2. And so when I make the binomial squared, I end up with and then here I get minus a positive 4. Notice again, the constants cancel. The constants will always cancel. They must. Which means everything we're left with has a delta x, which allows us to factor out the delta x, which allows us to cancel the delta x, which allows us to plug in the 0, and we're just left with negative 4. Do you notice something? When x is 1, the slope is 2. When x is 3, the slope is 6. When x is negative 2, the slope is negative 4. It's always double for this particular function. Ah, okay. So then, if I wanted to know what the slopes were for f of x equals x squared, rather than constantly plugging in numbers, the best approach would be this. Use a generic x1 or just x. Watch what's going to happen. Let me kind of recap this. So instead of plugging a specific value into the x1 and having to go through that process over and over again, if you want to know slopes, plural, for a particular function, allow just a generic x to be used instead of a specific x1 value. This gives me the limit as delta x approaches 0 for, again, we're going to plug this in, we're going to square it. Notice, delta x squared plus 2x delta x plus x squared. Square the first, square the last, multiply, and double. Minus whatever f of x is. We don't have to plug anything, it's just the x squared. Notice it's not constants that cancel, but I still get that canceling effect at the back end, so that everything that's left has a delta x in it. Again, I can either factor out the delta x, or I can straight up divide by delta x. If I just straight up divide by delta x squared divided by delta x, 2x delta x divided by delta x, 2x. When I plug in a 0, notice the limit is 2x. That's the first derivative of this function. Here's how we'll notate it. Write this in your notes. F prime of x is the first derivative. So f of x is my function, f prime of x would be the first derivative. If it's a g of x, then it's g prime of x. That prime notation, that little tick mark, means the first derivative. And 2x is the first derivative. So for this particular function, the slope of the tangent line is going to be double whatever x value I pick. And now instead of plugging in a 1, and then plugging in a 3, and then plugging in a negative, I just do this process once. No matter what x value I want, I know what the relationship is. Does that make sense? Let's take a look at another function here. Let's suppose we had a function of x is equal to 3x plus 2x squared. This one's going to get pretty ghastly, okay? Stay with me here. I think I'm going to need a little bit bigger piece of chalk. All right? So we want to know what is the first derivative equation. We're not going to plug in a specific value. We're just going to write it out with an x generically in here. All right? So we want to know the slope of the tangent line, which means that's going to equal the limit as delta x approaches 0, and then actually let's say the formula together here. The slope of the tangent line equals the limit as delta x approaches 0 for f of delta x plus x minus f of x all over delta x. Again, the slope of the tangent equals the limit as delta x approaches 0 for f of delta x plus x minus f of x all over delta x. So I'm going to have f of delta x plus x minus f of x all over delta x. Okay, so that's the limit as delta x approaches 0. Now here's where the fun begins. I'm going to have to take delta x plus x, plug it in here and here, because that's what function notation tells me to do. If this said f of 5, I'd plug in a 5 here and here. If it said f of 2, I'd plug in a 2 here and here. It says f of delta x plus x. So I plug delta x plus x here and here. When I plug it here, what do I have to do? Distribute the 3 to get 3 delta x plus 3x. If I plug it in here, I have to first square it, then multiply 2. Well, what would I get if I squared it?
Delta x squared.
X delta x, right? 2x delta x plus x squared, right? Square the first, square the last, multiply and double. But then I got to distribute a 2 through all of that. That's going to give me what, Jane?
2 delta x squared plus 4x delta x plus 2x squared.
All right? And then it says minus f of x. That means minus all of that. But do we ever really subtract? We add the inverse. So let's make the inverse of all of that. Quentin?
Minus 3x minus 2x squared.
Right, negative 3x, negative 2x squared. All over delta x. Do you see what we did?
Mm-hmm.
Now, here's the fun part. If it doesn't have a delta x, it better cancel or you did something wrong. It's a great way to check your process halfway through. What cancels?
3x and 2x squared.
The 3x and the 3x, negative 3x, the 2x squared and the negative 2x squared. And you see that everything that's left has a delta x in it. So what I'm going to do is I'm going to actually divide everything by delta x. So that I have the limit as the delta x is approaching 0. It's not going to be a fraction anymore. Divide 3 delta x by delta x.
3.
Divide 2 delta x squared by delta x.
2
Delta x.
And divide 4x delta x by delta x.
4x.
And if we evaluate where delta x is 0, what am I left with?
3 plus 4x.
3 plus 4x. That's the first derivative. Or, we wanted to write it in descending order, we could say 4x plus 3. The original wasn't in descending order. This is my first derivative. So if we came to this function, I said, what is the slope of the tangent line when x equals 1? Well, come to the first derivative and plug in a 1. What do I get? 7. But what about when x is negative 1? We'll plug in a negative 1 into the first derivative. Negative 1. What about if x is negative 2?
Negative 5.
Negative 5. And you see that by finding a derivative equation, man, you can crank out slopes really quickly. What about if x is 0? What's the slope? 3. Man, you just fly through them once you get the actual equation or function, if you will, of the first derivative. And the key again is instead of plugging in numbers, just leave x's. Work the process through until you can evaluate the limit, and whatever you're left with is the equation of the first derivative. Questions on that? Turn to page 314 in your textbooks. Page 314 in your textbooks. And let's take a look at number 1, letter A. Number 1, letter A. Go and jot the function down on your paper. And we're going to find the first derivative equation rather than the slopes at specific points. That way we can find a lot of points all at once. Because I believe the instructions, if I could read the instructions if you would there, Quentin.
Find the slope of the tangent for each function at points corresponding to x equals negative 3, 0, and 3 using the tangent equals limit when delta x approaches 0, f of x, or f times x1 plus
You were right, f of x1 plus delta x.
Minus f of x all over delta x.
Good. Now again, we're not going to use x sub 1 because we're not going to plug in negative 3, 0, and 3. We're going to find the equation first. We're just going to use x. Also, they do x plus delta x, I do delta x plus x. It really doesn't make a difference. Addition is commutative, but their formula is written slightly differently than the way I write it. All right, so we've got our function of x is 2x plus 3. We want to know the equation of the first derivative. And to find it, we're going to use, say it with me, class, the slope of the tangent equals the limit as delta x approaches 0 for f of delta x plus x minus f of x all over delta x. All right, so what we need to do is take the limit as delta x approaches 0. The denominator is just going to stay at delta x, right? Because there's no functions in the bottom. But the top, I need to come to my original function, and where it says x class, I plug in.
2x plus 3.
Where it says x, I plug in delta x plus x, because it's f of that. Well, what would be f of delta x plus x?
2 delta x plus 2x plus 3.
Good. 2 delta x plus 2x plus 3. Distribute the 2 and then keep the 3. 2 delta x plus 2x plus 3. Then it says minus f of x. That's minus that, or add the inverse of that, class.
Negative 2x, negative 3.
Negative 2x, negative 3. Cancel away the
Negative 2x, or 2x. Negative 3.
and now all I'm left with is a 2 delta x over 2x,
2.
and all I get is 2. There's not even a place to evaluate delta x as 0. It's just 2. You know what that means? No matter what point you pick on this function, the slope is always going to be 2. Now you knew that. Because this is in slope-intercept form, isn't it? Y equals mx plus b. Well, we don't say y, we say f of x. M is 2 for every point on that straight line. Of course we knew the slope was 2. But now we see it through the calculus method. Now, granted, I'm not going to give you linear, okay, because that's insulting. But for instance, I'll look at letter B. What's going to be the first derivative for any point? Negative 1. It's a linear function. I know it's going to be negative 1, but for practice sake, since we know the answer already, we'll know if we screwed something up. Let's try letter B. We'll take the same approach. F of x. Oh, by the way, we were supposed to find the slope when x was negative 3, 0, and 3, weren't we? Go back to real quick where we had said that the first derivative was 2, right? So when it says find the slope of the tangent when x is 3, that means find the first derivative of 3. Slope of the tangent when x is 0, find the first derivative of 0. Slope of the tangent when x is negative 3, find the first derivative at negative 3. So if f prime of x is 2, what's f prime of 3? 2. What's f prime of 0?
2.
What's f prime of 3? 2. Because there's nowhere to plug it in, so of course it's just 2, like the constant function we saw in the homework last night. See how this is setting it up? Okay, so let's go to the next one now. F of x equals negative x negative 4. And again, I know we already know the answer, but let's go through it anyway. We want the first derivative or the slope of the tangent. So let's see how the math works out. For f of delta x plus x, what should I write, Jamie? What if it's at f of a? What would I write, Jamie?
You write a delta x plus.
No, if this just said f of a, forget that over there for a minute. F of x is negative x negative 4. Find f of a.
Negative a, negative 4.
Right, if I said find f of 7, I would have
Negative 7, it'd be negative 1.
negative 1 because it's negative 7, negative 4. If I said find f of delta g, what would that be?
Negative delta g minus 4.
Right, so if I say f of delta x plus x, what's it going to be?
Negative delta x, negative 4.
Perfect. Negative delta x plus x, negative 4, or as you said, negative x, negative delta x, negative 4. Negative changes the sign of the delta x plus x, and the negative 4 stays along for the right. That was really sloppily written, so let's try that again. So far, so good. Quentin, follow what we did with Jamie there, okay? And then it says minus f of x. And to me, this is the easy part because you just take whatever function they give you and change all the signs.
Plus x plus 4.
Plus x plus 4. All over, class. Conveniently, we cancel away. And all I'm left with is negative delta x over delta x, but those cancel to leave me with negative 1. And as we knew that would be the case, that's the first derivative. So what is the slope, f prime, of 3?
Negative 1.
What's the slope at 0?
Negative 1.
What's the slope at negative 3?
Negative 1.
Because it's a straight line equation, the slope's always going to be negative 1. So far, so good? All right, now the fun part comes in something like letter, and we're almost out of time. Tell you what, let's do this. Tackle page 314, number 1C for homework. Tackle it, see how it goes. If you botch it, don't beat yourself up, but try page 314, number 1C. I also want you to copy down that first derivative equation 3 more times for your homework. That way you'll have it memorized really well by the time we come in tomorrow. Okay, so copy the first derivative equation 3 more times, and do page 314, number 1, letter C. Again, if you struggle with it, don't beat yourself up, but I'm curious to see how we do, and we'll work on more of this tomorrow. All right, have a wonderful rest of your day, and you are dismissed.